I have one student coming, and they are going to share screen. Have a couple of other students? I don't know. Okay, so what today we will do is we will start with a new topic. And I didn't exactly follow textbook order, okay, because I think it's the order the textbook arrange is kind of not too logical to me, okay. Hold on, let me get to the other students coming. So today we will start with binary search tree. Someone needs to turn off the your audio. So binary search tree. It's a new data structure. Okay, we will learn, and it's in our textbook chapter 25, I believe. Okay, in textbook. So if you want to read a textbook, it's in chapter 25. And some of the students here in this class may already know some ideas about binary search tree because last spring we covered a little bit, okay? So then for you, it's just a review, okay? But because last semester we didn't get a chance to learn binary search tree, so I need to repeat this part. So a lot of time you will see this as BST, okay? So that's what we will learn. And what we will learn is linked way implementation, okay? Linked implementation. So it's a little bit of more complicated compared with linked list. Is it? We learned the simple linked list. So linked list, it's a linear data structure. And based on the name for BST, for binary search tree, then you know that it has a tree. So it's a tree data structure. And you can, hold on, we have student coming. And because it's a tree data structure, so you can imagine that it's more complicated, okay, more complicated. And then let's see. So first, how about let me draw a tree, okay, so that you have some basic idea. So I will draw it like this. So 55, and then I will have 50. Then over here I have 60. And then over here I have 38. And here is 51. Here I have 39. And here I have 57. Here I have 65. And here I have 59. So if you take a look, so far we haven't learned any data structure covered can be able to store this kind of diagram, is it? So, and I should also draw something like this. So the arrow, okay. And so this is a case of a binary search tree. Search tree. As if you take a look, a close look, you will find what? So over here, this is considered. This is considered as a node. As it previously we learned linked list. So for simply linked list. So this is a node. And then you have information, you have the next part, etc. And it points to the next node. So that's for the simple linked list. And I remember in your assignment, you also have some linked list, two-way as it linked list. Then you have next, you also have previous. But no matter what, it's still linear structure. And if you take a look, then this is considered a node. It has definitely has information part. But you can find each node can connect with two nodes. Hold on. One more student coming. And over here, so each node can connect with two other nodes, And if you take like it's kind of repeating this kind of pattern, each node connect with two other nodes, And this kind of data structure, we call it a binary tree if it's just connected with two nodes, okay? And if you take another look, you can also find like this 55, this node, it's at the very top, At the very top, it doesn't have any, so no incoming. And we call like the arrow an arc. Okay, so no incoming arc, but it has outgoing. So this is outgoing arc. And for 50, okay, for node 55, okay, because this arrow for node 60, then it's considered as incoming arc, But anyway, for this specific node, it doesn't have any incoming arc, And this node, we call it a root node. And it's a kind of tree, and it's upside down tree, So that's why we call this specific node as a root node. So basically in a binary tree, you can see once you know the root node, you know the complete tree, because based on all of the outgoing arc, you can get to all of the other nodes. Is it just like a linked list? Once you know the first node, you know the complete linked list. Okay, so this is the definition for root node, no incoming arc, okay? And for all of the other nodes, over here, it has incoming arc, it also has outgoing arc, okay? But if we take a look like this node has incoming arc, but it doesn't have outgoing, so no outgoing arc. So this kind of node, we call it what? A leaf node. That's just like the tree, the tree. And the leaf doesn't have any more branch, so that's why we call it leaf node, okay? So this is root node and the leaf node. We kind of have the concept. And also within tree structure, so each of this, so each of the, over here, the circle I draw, and within it, I have some number. Each of this, we call it a node. Okay, a node. And in binary search tree case, it's called bin node. Bin node, binary node, bin node. Hold on, I need to get this student admit. And where is my, okay. Okay, so this is called a node. Then how about those arrows? Is it those lines connected with two nodes? And generally we can call it an arc or an edge. Okay, so that's the name. And within this diagram, and it's called binary search tree. This binary means it should have some two of something. That's also what does that binary mean? So this binary means each bean node can have at most, be careful, okay, at most two branches. And we have some name for these branches. Okay, so basically two subtrees. Okay, so regarding node 55, the root node, and its right branch, the complete right branch, okay, this is called a subtree. And in this case, it's a left subtree. Left subtree, okay. And its right branch, so the complete branch, okay, this is called a right subtree. Okay, so like here, say each node can have at most two subtrees. That's why we call it binary tree. Okay, it has two branches, okay, two subtree. And similar, is it for node 50, it also has left subtree and the right subtree, is it? And for node 38, it only has right subtree, is it? And for a leaf node, it doesn't have any subtree, is it? So similar for each of the node, like over here for 60, it has right subtree or left subtree and right subtree. And for 57, it has right subtree, okay. So this is regarding subtree. And then we have some other concept. And also if you take a look like node 50 and the node 65, is it 60? There should have some relationship between these two nodes, is it? And node 60 is node 55 lead to node 60, is it? So the relationship between these two, we call node 50 parent node. And with respect to node 60, okay, and then node 60 regarding node 50 is called child node. Okay, but regarding like between node 60 to node 57, then the relationship is node 60 is parent node of node 57, is it? And node 57 is a child node of node 60. Okay, node 60. So that describes the relationship between the nodes. Okay, and I think that's the basic information about a binary tree. Okay, so what here shows is a binary tree. So each node has at most two subtree, okay? So that's the concept of binary tree. But over here, if you take, we call it binary, not all binary tree is binary search tree, okay? So in this chapter, we discuss is focus on binary search tree. So what is this binary search tree? So it has some special feature. If you take a look, node 50 is a root node. All of the nodes on its left is what? Is less than 50. This is less than 50, is less than 51, is less than. Okay, so when you arrange the number, if the number is less than 55, you need to put it on, let it grow in the left subtree. Okay. And if you take a look, 60, 57, 65, 59, all of those numbers, what? They are greater than 55. So all its right subtree are greater than the node. So it has always had this pattern. Is it regarding node 60? Its left subtree of the nodes, their contents are less than 60. And regarding its right subtree, all of the nodes has the value that's greater than the node itself. Okay, so that's, then if you have the binary tree arranged like in this case, then we call it binary search tree. Okay, binary search tree. And then just think it has some advantage in this case for searching. Is it? Because if you say, oh, I want to find a number like 35, then you don't need to go to right subtree. Is it? You just go 55, so left subtree. Is it? Each time you just go to the left. Is it? Yeah. So that's why we call it a binary search tree. And then just think about when you have a new item, new number, suppose in this case 35, and where are we going to let it grow? So you are going to start from the root node as it compare with the root node is less than, so you go to the left. Then you compare with this node. It's less than, so you go to the left. Is it? And then you compare with 38. It is what? It's less than. So you should go to the left. But the left doesn't have any branch. Is it? So you can let it grow here, 35. Is it? So that's how each time when you have a new item, how do you add it to the tree? Is it? So it's based on if it's greater or less than the specific node's contents. And then you let it grow as a leaf node, either left or to the right, as either the left leaf node or the right leaf node. Okay, so this is regarding the tree, binary search tree, the general concept. Okay, general concept. And then what next? Let's take a look. Okay, for the binary search tree. So the basic building unit. Building unit, as we just discussed, is a bin node. Is it? So what the bin node will look like? Then it should look like something like this. Is it? So it has some information stored, but it has two outgoing arc, is a two branch. So in this case, you have one point to the left, and then you have another one point to the right. Is it? To the right. Okay, so how about let's do this quiz question. The first quiz question. So what do you think the type of left and right, the data type, left and right should be? Left and right should be, assuming, I know in CS2 you learned, is it generic? Suppose the type is a generic T. So is left type of T, right type of T?
Yes.
What's the data type for left and right?
T.
T? What's the answer? the left and the right.
Generic.
No,
Yeah, yeah, please go ahead.
I think no T.
Yeah, it should be what? And we call it what? We call it a bin node. Is it? So the type should be bin node. Just like a linked list, is it? It's node, is it? So the type should be bin node. Okay, so be careful, it's not a T, okay? It's a bin node type. Okay, so that's the building unit. Okay, building, we understand this. And what next we can discuss is, and then generally speaking, whenever we discuss some data structure, is it? So we, in CS2, we learn also called collection, because you want to use it to store a group of items, that group of the items. And generally speaking, do you still remember normally what kind of operations we care? Operations, normally speaking, what we care about the collection. So who kind of still remember? Generally,
library collection?
Yeah, generally speaking, any kind of data structure.
Sort.
General operation means you start to build this collection. You can do something on this collection.
Add.
Like for what?
Add.
Yeah, very good. Yeah, add. Is it? That's generally speaking, we care about. Is it? Add, and then opposite to add is what? Opposite to add. Add is you want to add a new item. Opposite to it is what? Generally. Delete. Yeah, delete. Is it? Or remove. Is it? Either call remove or delete. Is it? What's some other interesting operation, generally speaking?
Guide.
Right?
Guide.
Index of.
Yeah, index of kind of. That's what generally speaking, it's some search. Is that you look for some item. Is it? And what is next? And if you want a lot of time, you remember that special word, you want to node by node visit?
Transfers?
Yeah, it's a traverse, is it? Node by node visit, is it similar? Okay, so in binary search tree, okay, those generally speaking, the most important operation you need to provide, okay, to build the binary search tree data structure. It should allow you to add a new item, should allow you to remove some item, should allow you to do the search, should also allow you to do a visit, node by node visit. But you will see, for tree structure, it's completely different from what we have learned so far, no matter it's array or list, or stack or queue. They are all linear, etc. So whenever you do node by node visit, it's not a big deal for all of those. And for the tree, there's two branch. How do we do node by node visit, etc. So that's a kind of the concept we will see. So anyway, general operation is going to be of this. Okay, so next let's take a look. Then we can discuss one by one. Just theoretically, okay, theoretically. And then how about let's just take a look. So we have that sequence of numbers. Suppose I have 55, then 50, then 38, 51, 39, 60, 57, 57, then 65, then 59. Suppose I have this sequence of numbers, is it? And I want it to be stored. So store them in a binary search tree. Is it binary search tree? Then how do we do it? Then you need to start to build the tree. Is it? So the very first step is you have this first node created. You need to create this node, bin node. Is it? Then you have its left, has its right. Is it? So that's the first one. Then you come to 50. Is it? So where do you think I should let 50 go? Go to left or go to right?
Left.
Left, is it? Okay, so I need to draw it because it's needed to keep growing, is it? So then you're going to have node 50 and it's some node, is it bin node you create? And you need to also connect it to node 55, is it? And then 38, where should 38 go? So you start with 55. So it's go left or go to right? 38.
Left.
Go to left. Okay, so you're going to follow, go to left. Then you see 50. When you see 50, it should go left or should go right?
Left.
So it should still go left, is it? So here is 38, is it? And you create a new node. Okay, then 51 comes. So you still start. So we always start at root node. Is it when we do insert, or we call it add? Is it we always start at root node? Is it this? Okay, 51 starts, it's go to left or go to right?
Left.
So go to left, and then you come to node 50. Then you should go left or go to right?
Right.
Left, 51. Yeah, it should go to right. It's greater, is it? So it should go to right, 51, is it? So now you're done with this. So I'm done with all the number. And then 39. 39, you start at the root node. Go to left or go to right?
Left.
Go to left. Then you come to 50. So go to 50's left or go to 50's right?
Left.
Go to left. Then you come to 38. Go to 38's left or right?
Right.
Let's go to right. Okay, so you have 39. And then so this one also done. Then how about 60? Go to left or go to right?
Right.
Go to right. So we have 60. So I'm going to draw a simpler way. Okay. And then 57. Go to left or go to right?
Left.
Go to left. Yeah. So here you have 57 and 65. From 55, go to right. And
Right,
it's greater
right.
than it's right. Yeah, 65. And then 59, start at 55. So go to right. And it's less than, so go to compare with 50, it's greater. So it's 59. Is it? So you get the tree build up. Is it? Once you have the tree build up, then assume you want to search an item. Suppose I want you to find 57. I want you to tell me where 57 is. Is it? So then how do we do it? You start at the root node. Is it? It's you compare 57 with 55. It's greater than 55. So can it be possible to be on the left subtree? There is no way, is it? So you can completely forget the left subtree. Go to the right subtree. Then you reach node 60. You compare with node 60, is it? It's less than 60, so it should go to left. Is it go to left? So you now reach the node. you compare with 57, it is a node, so you find it. Then you find it, okay. And suppose we also find some other node like 90. Then similar, as that you start as a root node, it's greater than 50, so you should go to right. And then compare with 60, it's greater than 60, so you should do the right. It's greater than 65, so you go to right. But the right is what? Is a null node. Is it? So that means this one doesn't exist, okay, in this tree. So that's how we go with search in the binary search tree, okay, binary search tree. Okay, and we already learned algorithm analysis, is it? So time complexity. And then based on what we just discussed, what do you think the search operation? The search operations time complexity. What do you think?
Is
Is
it
it-
like
Yeah,
similar
please.
to a binary search?
Yeah, it's kind of like a binary search.
So
Yeah.
wouldn't that be log n?
Yeah, so it should be log 2n. Very good. Is it log 2n? Is it because anyway, each time you just go halfway? Is it you just do half, the other half you throw? Is it kind of like the binary search? Is it binary search? Okay, so it's log 2n, okay, for the search, for the binary search tree case. But okay, so then this log 2n for BS binary search tree, is it? So is this going to be best case, average case, or worst case? Anyone knows?
Average case?
Yes, very good. It's average case. Is it? It's the average case, log 2n. And what's the best scenario for average case for binary search tree?
01.
No, what I mean is the tree itself. What's the best scenario for the average case?
For the best case or for the average case?
No, I'm sorry. Here, I didn't put the question clear. What I mean, among average case, is it among average case, what's the perfect scenario for the log 2n?
Half and half, half the nodes on one side, half nodes on the other side?
Very good. Yeah, very, very good. So it's balanced. Yeah, it's balanced. Is it? It's balanced. Because if your tree is not balanced, tilted one way, you cannot get log 2n exactly. Is it? So that's also later topic in this course. It's a balanced tree. Okay, then it's log 2n exactly. Is that exactly? Okay, and assuming it's the balanced tree. Okay, it's a balanced tree. So regarding the tree, and we can also see the tree has levels, is it? Okay, so we can view this is level 1, is it? And this is level 2, is it? And all of this going to be level 3. And this is going to be level 4. Is it level? So that means kind of they are at the same level, the nodes. Is it? So anyone kind of get the idea how do we find the number of levels for a binary search tree? Also the best scenario. So best scenario. So for a perfect tree, okay, for a perfectly balanced tree, how do you find the number of levels? Basically, how deep the tree can grow.
Log 2n.
Very good. Yeah, it's log 2n, is it? So the number of levels completely log 2n, is it? Yeah, it's just how many times kind of it can split by 2, is it? It's a similar concept. So if you want to know the number of levels, just log 2n, but that's just perfectly balanced. Okay, if it's not perfectly balanced, it's not always true, is it? Because even like something like this, is it? You have 10, then 9, then 8, 7, 6. This is also a binary search tree. You cannot say it's not a binary search tree, is it? But it's skewed in one way. Is it skewed? Or you may just have a single node here. Is it? That's kind of tilted. Is it? Then in this case, whenever you do search, that's going to be what kind of case? Worst case. Is it? Worst case. Is it? So tilted one way and always, and it's at the very end, the leaf node. Is it? Then it's kind of just a linear search. Is it linear search? Okay. Okay, so this is the idea about binary search tree.
Dr. Liu.
Yeah, please.
I don't know if like when you would use this, but what would like can you have multiple duplicates of the same entry in a binary search tree?
Okay, very good. Okay, very good question. No. Okay, very, very good. Okay, so yeah, I forgot to mention this. Very good reminder. So for binary search tree, each node is unique. Or we a lot of time we said whatever the node contains the information. So nodes information, we call it a key. Okay, so the key is always unique. Am I right? Unique? Did I write correct?
Yes.
Unique. Okay, because right now too much prompt whenever you type, is it? So I kind of see it's not like unique. Okay, so anyway, all of the key in a binary search tree must be unique. It doesn't allow repetitive. So if the item is already in the tree, then it's not going to be stored. It's just stored once. Okay, once. Very good question. Okay. Okay, if there is no other question, then how about let's take a look at some other case. Okay. We already discussed the search, is that? Okay, and the next, let's see, before we move on, let's first build the tree. Okay, I will just draw the tree. We have G, and then I have F, and then I have J. And then I have A. Okay, after that I have E. And I have H. And I have O. Okay, so anyway, this is also a binary search tree. But what is the key is some letter. That's not a number. That's also fine. That's also fine. Okay, let me erase this. Okay, and what we already discussed the search, insert, is it? And now we want to discuss traversing. Traversing, what is traversing? So node by node visit. Okay, but for binary search tree, how do we do node by node visit? Is it, how do we follow? Is it, so this is going to be interesting, is it? So whenever we discuss binary search trees traversing, there are three kinds, generally speaking, okay, we use. One is called, we call in order traverse. And the other one is called pre-order traverse. And the third one is post-order traverse. Okay, so what is in-order traversing? In-order traversing means you want to visit left node first, and then node, then right. That's the sequence you're going to follow. Pre-order is node first, then left, then right. Okay, post-order is left first, right next, node last. Okay, so that's the definition for different kinds of traversing, okay? So next, let's see, what does, let's start with in order traversing, okay? In order traversing says left first, but whenever, you see, it's a tree, is it? And for the tree, we only have that single instance root node. So you know the root node, basically we said you know the whole tree. And why we see that? And so you start as a root node, is it? But it says you visit left first. So here it's not you visit, here it's you processing. Okay, we process, so you're going to do some calculation or you're going to do something with the key. Okay, with the key. Okay, so here left first, so this is not left. It still has left node. So I'm going to follow its left node, reach to F. And F still have left node, so I need to go further left. And then I go A's left. A doesn't have left, is it? So it's a null. So you don't need processing, is it? And then what? Then node. Okay, so then I go back to node. So left node. Okay, suppose what I'm going to do, for this processing is to output. Okay, so left, I don't have anything output, it's empty. Then I go back to node. Okay, node is who? Is A, is it? So I output. And then what? Then I go to right. Is it? Okay, right is what? Is a leaf node. Be careful here, okay. It is a leaf node, so I can what? I can output it. And what? And after this, I finish regarding, this is node, is it? F is node. I finish its left tree. Left subtree, is it? So following the sequence, so I'm already done with the left. Next is what? Is node, is it? So I need to output what? Output F, the node. And then I need to go to its right. Right is what? Is empty, so I have nothing to output. And then what? I basically finish this left subtree. Left subtree, is it? So I need to do what? I need to go back to node. Node is what? Is G. Okay, and then I do what? I move to right. Is it? I move to right. Should I output J?
Not yet.
Not yet. Very good. Yeah. Where should I go?
Right.
Yeah, I should go to left. Is it? You go to the right. And this node still has what? Then you need to go back. Whenever you see the node, you need to follow left node right. So I what? I go to left. Is it left is what? It's H. After I finish H, I go back. Is it? Node J. Is it? After I finish J, I go what? I go to right. Oh, is it? I go right. And I finish this node. Is it? And you also finish the right, the node, root node's right subtree. Is it? You complete finish. Is it? So that's the output of this in order traversing. Is it in order traversing? And so basically here, did you see you kind of, you finish left, then you go back to node, then you go to right, and then you finish left subtree, you move back to node. And this kind of concept, if you recall previously in our algorithm discussing, we also kind of see some algorithm also kind of use this kind of idea. Do you also kind of remember what
You mean
is that?
backtracking?
Yes, very good. So this is kind of like the backtracking, is it? You backtrack, is it? You finish and then you move to the previous level, is it? Yeah, so this is also kind of the backtracking concept, okay? And then with the in order traversing, did you find some special thing? So among the tree, is it among the tree for the output, who is going to be, who is for the output, who is first? And who is last? For in order traversing, who is going to be the first?
The
output?
farthest left and the farthest right.
Yes, that's very, very good. Is it the first, if you take a look, A, it's the leftmost node. Is it the leftmost? Is it leftmost node's key? And for O, it's what? It's a rightmost. And rightmost here is, yeah, the rightmost node. Rightmost node, is it? And also it's regarding its key, is it? So that's the output, is it? And generally the output has some special pattern. Anyone see the pattern for the output?
It is in ascending order.
Very, very good. It's in ascending order. Is it? It's in ascending order, if you see. So in order traversing for binary search tree basically give you what? Give you ascending order, okay? So this is in order traversing. I needed to clear this, it's too messy, okay? I need to redraw it. Let's redraw the tree. Okay, so we have G here. And then I have F. And the same level has J. And then I have A. And after A, I have E. And here J, I have two branch, H and O. Okay, so now let's take a look. So we already finished in order. Okay, so let's take a look pre-order. A pre-order traversing is following the order of node first, then left, then right. Okay, then left, then right. So let's come back again to see. So what we are going to do here, suppose we want to output keys in the binary search tree, okay? So we start at root node, G. So should I output G? So suppose here is output. Okay, I hear someone said yes, is it? So we output G. And then what? Based on what we previously discussed in order. Where should I go?
Left.
Left, very good. And we see F. What should we do? I should continue visiting.
Print F.
Yes, very good. We should print F. Is it? Because what? Because it's node. You got to the node. Is it? So you need to output immediately. And then what? You go to left or go to right? Go to left. Is it? Then we see A. What should we do? We visit or we output A?
Output.
Output A. Yeah, very good. After I output A is process. What should I do? Should I backtrack or should I move on?
Move to E.
Move to the right. Is it because it doesn't have left? It has, if it has left, you should go left. Is it? Because it doesn't have left. So following node left, nothing, and go right. Is it? And we see E, what should we do?
Print.
Print, is it? Yeah, output. And now what? You finished regarding node A, all of its node left and right. And regarding, so this comes back, the backtracking concept, is it? Then regarding node F already visit, its left subtree also visit. What should you do? You should go to the right, but the right is empty. Is it? So you don't need to worry, is it? Now F is done, is it? Its complete subtree is done. So come back to node G, is it? And node G, it's left, it's done. The itself is done. So node is done, left is done, then what? You should move to node G's right. Is it node G's right? Okay, node G's right, we come to J. What should I do with J?
Print J.
I should, yeah, please.
Print J.
Yeah, print out J. Is it? And then what?
Go to left.
Go to left.
Print H.
Left is H, print out H. And then what?
Back to G and traverse it to right.
Right.
Yeah.
Is it? Oh, is it? And then this whole right subtree is also done. Is it? So node left and right. Is it? So this is also done. Is it also done? Okay, so this is called pre-order. Is it? And then if we take a look regarding pre-order, it's also involved backtracking concept. Is it? And if we take a look at pre-order, so who is going to be the first node to be visited? Output. So first output and also last output maybe.
First node either first output either always either node or root. And the last output always either
Yeah, it should be root node. Is it? Yeah, it's G. Is it? Then how about last output?
always is right child root.
Yeah, so the rightmost
Yeah.
leaf node. Is it? The rightmost leaf node. So that's the feature regarding pre-order traversing. Okay, pre-order traversing. Okay, we get this idea clear. And then next, let's take a look. The last traversing cases. Okay, so it's post order. Post order. Okay, for post order is what? Left, right, and node. Okay, so let's see. So we have G. And then let's see, F. And then we have J. And then we have A. After A, we have E. And oh, F, we don't have anything. And then over here, we have H. We have O. Okay, let me clear this out. And I think based on what we already discussed, in order and post order, can you try the output? Can anyone volunteer to do this? What should we do? Any volunteer?
First the output is E.
First output. Why? Can you just start from the beginning?
Yes,
Start
we
from
start at G and we go to left first. Is F and continue go to left. So right now we finish all the left. So we print root. So that is A. Print A.
Think about it.
Print
Still
E.
go to the right though.
reach. So now we reach A.
Yeah.
Now we are here.
Yeah.
Regarding this one, then what you do?
Print
You go
right.
You go to left.
Yeah.
Left is empty.
Yes.
Then what? Left, empty. Then what?
Print
Right.
Right.
So what should I write here?
E.
Output. You should output what? E, is it? Because left is nothing. You go to right. Right, you have something, E. Is it? After E, what do you do?
You output A. Well, you come back to node A, but then you
output A. Is it? Now you are done with the left. And then you are going to check F. Regarding node F, what should we do?
since there's no right.
Yeah, it's
we
no
output
right.
it.
Output F. Yeah, very good. And then F is done. Should I output G?
No.
No, very good. Yeah, because what? Because you need it. So the left G is left is done. Then what? You need to do what?
Go
So
right.
now the current node we are dealing is G. So regarding G, what should we do? We are done with its left, is it? Done with G's left. Then you move to what?
J.
J. Yeah, very good. You move to its right. Is it? Okay, should I output J?
No, we go left.
You go left. Yeah, very good. So we output H. After H, what next?
We go back to J and then to O.
O. So you first output O. Is it? After you go finish O, so regarding J, okay, H is done. O is done. Then what? You go back to this node, J. Is it? Okay, then this right tree, subtree down. After right subtree down, what should you do? Left or
Look for
right?
the root node.
Yeah, you visit the root node. Is it? And then you complete the post order. Is it? So then for the post order, then who is the last node? Who is last output?
Root node.
Yeah, it's going to be the root node. Okay, be very careful. Okay, be very careful. The right node. Okay, the first node is going to be the rightmost branches, or leftmost branch is right node. Is it node E? Is it? Okay, but that's not some very basic feature. Okay. So this is regarding traversing. Okay, we are done with traversing. And so today what we are going to do is just go over all of the concepts. Okay, once we are clear about concept, next we are going to go to coding. Because for the data structure, a lot of parts regarding concept. And we learned search, insert, traverse. So the last one we haven't discussed is what? Is delete, or we call it remove. Okay, so how do we deal with that? Let's take a look. Okay, this is a little bit complicated. So we have node J, then we have F, then we have J. Okay, after F, then we have A. Okay, after A, then we have E. Okay, after E, then we have C. After C, then we have B. Then we also have D, okay? And after that, we have what? We have H, then we have O. Okay, after H, we have I. And after O, then we have M, and we have P, okay? And after M, we have, okay, we have N. After K, we have L. Okay, so this is our tree, okay? This is our tree. So we are going to delete. And for binary search, delete is a little bit of complicated. There are 3 cases you needed to discuss, okay? Case 1, because you cannot just delete a node, is it? If you recall linked list, you still have some cases you need to think about, is it? So case 1 is if the key is at leaf node. Okay, suppose we want to delete D. And so whenever you want to delete, the very first thing you need to do is what? Think about it. Because whenever you write your code is you are going to remove T item. Is it? So the very first thing you need to do is what? Whenever you do remove.
Access the root node.
Yeah, start with a root node. And so basically what you need to do is kind of generally speaking, whenever you want to delete, you need to search first. Is it? You need to find where the item is. Is it to search first to find where it is? Is it where it is? So in our case, it's D. Is it? So we just follow whatever we discuss and search. Is it? So you can go, find. Okay, we find it. You find it and you, based on its left and right, are all known. So you know it's a leaf node. So if it's a leaf node, then it's easy to do delete. Is it? So think about what should we do for the delete. That means I get rid of this node from this tree.
Go back and change C's right pointer
Yes,
to
yes,
null.
yes, very good. Is it? So this is node. You found it. You're going to delete. C is what? C is D's what? Parent. Is it? So what you are going to do is you just set the parent's right to null. Is it? So parents right equal to null. You just set this. Is it? Then this node will be deleted. But in Java, did we clear node D from memory? So is it cleared from memory?
No.
And also which memory? We learned we have stack memory and we have heap memory. Is it cleared?
Not yet. Maybe waiting for garbage collection.
Yeah, it's not. Is it in Java? It's not cleared from memory. Okay, because Java virtual machine will take care of the garbage. So garbage collection will take care. Okay. So it's garbage collection will take care of this. Okay. So this case is the case. It's kind of easy. You just set. If it's on the left, then you just set parents left to null. In this case, right. So you set the right to null. Okay, second case. Case 2. Okay, case 2, suppose, so let's see. Okay. Suppose I want to delete E. Is it? So node only has one subtree. So the node doesn't have two subtree, just has a single subtree. Node E. Can I just how do I remove? Is it? So this is a node you're going to delete. The node just has a single, just has a left tree. Is it? So in this case, it only has left subtree. So how do I do the delete? Because it, yeah, please.
A dot right equal C.
Yes, okay. So what you can do is, but yeah, but there is no C. That C is what? C is what? Is left child. Is it? So basically you need to, so this is parent node. Is it? So parents right, then it's going to be what? To nose. Nose what? Nose left. Is it? So
But shouldn't we
you-
compare it first, like A and C?
Yeah, that's a very good
What if
question.
C is on the left?
Hold on, okay, hold on.
Well,
Let
it's
me-
already sorted to the right because when we were adding C to the list, it had to go right in the first place. So we know that it can go on the right anyway.
That's a very good discussion. Yeah, that's very, very good discussion.
really.
Okay. Yes, that's very, so in case of the, in case of this, if this node only has one subtree, let's say one subtree, anyway, this is on the node's left. Is it because anyway, you know the parent. When you do visiting, you can keep tracking the parent node. You keep tracking the parent node, and you know this node is on the parent's right. Is it? So that's why you set parent's right to this node's left. Then just, yeah, what I believe Nathan explained is that this C will not be on A's left. There is no way. Is it? Because what? Because this C subtree is E's subtree, and E is on A's right. Is it? So there is no way it can be less than A. Is it? Definitely, because the whole subtree, A's whole right subtree is going to be greater than A. Is it? So there is no way. So you don't need to worry about the comparison. You just directly connected its right to nose left. Okay, depends. It maybe it's right. Okay, but anyway. So anyway, so you just, because it only has one subtree, so you just connect that single child subtree. Okay, so this is this case. Okay, and the third case is, oh, we run out of time today. That's the most complicated case. Okay, so let me, this stop. Okay.